All right, so this is going to be our first video for the equations that are going to be on the final exam. And so what I want to do with these videos is to lay out all the equations that we need and talk about what their pieces are and how we use them. I'm not going to do any examples. I think there's plenty of examples for you guys to work on yourselves, but this will give you an outline of what the equations are. So to start with, chapter 2 and 4 are the one-dimensional and two-dimensional kinematics sections, and so I'm kind of putting those together here. So these are the equations that are going to relate your position, your velocity, your acceleration, and time. So to start with, we have these equations on the left that tell us all of the information we need. And to remind you what all of these symbols mean, x is going to be the position, v is going to be the velocity, and a is going to be the acceleration. Okay? So we've had a lot of practice with these equations, and this is just to remind you what they are. These are the equations that you'd use, of course, for, say, you had a ball and you dropped it. I know it's this high. How long is it going to take to get to the bottom? We know the acceleration is the acceleration due to gravity, which is g. If instead what we told you was, I have some position and another position, and I know how long it takes to get between these 2 points, what is the average velocity? This is the equation that you'd want to use. Okay? Or if instead I tell you an object has a velocity here and then it has a velocity here, what's the average acceleration? This is the equation that we want to use. Okay. Now, like I said, these equations can be generalized from one dimension to two dimension by saying that in two dimension, I just have two sets of these equations, one for x and one for y. So I can define instead the position vector r so that it has an equation in x that comes from here and an equation in y that also comes in from here. And so what we would do is we would say, okay, well, what are my initial position and velocity, and what is the acceleration in the x direction? And I would create an equation for x, and I would do the same thing in y. So it's my initial position in y, my initial velocity in y, what is my acceleration? We can also define a velocity vector in much the same way. So we have some x component of velocity that comes from this equation, and some y component of velocity that comes from this equation. The next set of equations that we have are going to be the ones for forces. And so that's going to be over chapters 5 and 6. Now, the most important equation here, and really probably the most important equation for the entire semester, if you don't learn anything else this semester, what you really need to learn is Newton's second law. And that says that the net force acting on an object, or the sum of the forces, is equal to the mass times acceleration. This was the equation that we used for when we had blocks on inclined planes. It's going to be what we're going to use when we have a system where we have some moment of inertia for a pulley and masses that are hanging off of it. It's a very, very important equation. So then we can ask ourselves, well, we want to sum the forces, but what are some of the forces that could be part of this sum of forces? The first one, then probably the most familiar to us, is going to be the gravitational force. And that's just to say that the force of gravity is going to be m times g. The next one that we have is the force of kinetic friction. The force of kinetic friction is going to be equal to the coefficient of kinetic friction times the normal force. And we remember the normal force is the contact force between a block, let's say, and a table. So I can draw a table here, and we know that the normal force is going to be perpendicular to the table. That's what normal means. Normal means perpendicular. So that would be an example of a normal force. And the last force that we have here is the force of static friction. Now, if you look at this equation for the force of static friction, you can see that it's very similar to the force of kinetic friction, with the exception of, rather than having an equality like we have for the force of kinetic friction, we have an inequality for the force of static friction. And what this tells us is that if something's at rest and I start to push it and I'm increasing that force, the force of static friction is always going to just exactly balance what force I apply to it until it reaches a maximum value and then the object starts to move. So if the force of static friction was always mu s times n, what that would say is that the force of friction could cause something to move in the opposite direction. And we know that that's something that's not true. Okay, so far when I'm talking about forces here, we've only really talked about going in a straight line, but we also discussed what happens when something goes in a circle. And so when something goes in a circle, we can still sum our forces exactly the same way that we did with our problems with blocks that are just on an inclined plane, let's say. But then, if something's going to move in a circle, it has a very special acceleration. And that acceleration is going to be the centripetal acceleration. And that says that the centripetal acceleration is going to be equal to its tangential velocity squared divided by the radius. And we saw a lot of problems with this when we talked about roller coasters. You go through a loop. If you're lucky, you can get Dr. Maris to say loop-to-loop. It's really funny. We also use this equation for the conical pendulum or a turntable. So anything that moves in a circle that we want to find what the acceleration is from a force, we use Newton's second law, and we say that the centripetal acceleration is going to be v squared divided by r. So this page is going to be all about work, energy, and momentum. So to start with, let's look at the definition of work. Work is defined to be F times d times the cosine of the angle between d and f. So F is the force, so we have some object, we apply force to it, it's going to move, some distance d, and to find what the work is done by that force, we take the product of the force, the distance it moves, and the cosine of the angle between the force and the distance, in the case that the force and the distance are not in the same direction. Okay? The next thing that we want to talk about is energy conservation and the work-energy theorem. So actually, I have this written in a different order than I'm going to talk about. So the next thing I want to talk about is the work-energy theorem, which is this one down here. So what the work-energy theorem says is if I can find what the work is done on an object by all forces, that total work is going to be equal to its change in kinetic energy. And we remember that translational kinetic energy is going to be this term here, this 1/2 mv squared. And so if I have something that starts here, it ends here, and there's some force that gets it to go from here to here, the total work done by that force is going to be equal to the change in kinetic energy. So the difference between the final kinetic energy and the initial kinetic energy. Okay. Now, we also talked about energy in the context of energy conservation, and this is when we had our energy bar charts. And that was to say that the initial energy is equal to the final energy. So if we had some state A and some state B, if energy is conserved, the energy in state A is equal to the energy in state B. And what we said was, in general, that the energy E is equal to the kinetic energy plus the potential energy. Now, we know what the kinetic energy is. It's the same term that we have in our work-energy theorem. But we haven't really explored what the meaning of this guy is. What is potential energy? Well, potential energy can come in many forms. Two of the forms that we talked about in this class are gravitational potential energy, which is what I have written here. So gravitational potential energy is going to be mgh, and spring potential energy. Spring potential energy is 1/2 k times x squared, where k is the coefficient of the spring constant. So how stiff or weak is the spring. Okay. So that's all on work and energy. Then we talked about linear momentum. So we remember, and it's kind of an intuitive way of understanding momentum because it's consistent with the way that we colloquially speak about momentum. And that's that the momentum of an object is going to be equal to its mass times its velocity. So this is our definition of momentum. And so let's talk about what this means. So if I have a bullet and it's something that's pretty light and it has a very large velocity, because the momentum is the product of the mass and the velocity, that bullet, you could say, has a pretty large momentum. Likewise, if I have a train car, the train car, it's not going to move as fast as the bullet, but it has a lot more mass. And so actually between those two, the train car has a much greater momentum because of how much larger the mass is. So when we talk about momentum, we typically talk about collisions. And so there are two types of collisions. There are perfectly elastic collisions and perfectly inelastic collisions. So in both of these cases, momentum is conserved. So what do I mean when I say elastic and inelastic? A perfectly elastic collision, one object's going to hit another object and it's going to bounce. And not only is it going to bounce, energy is conserved for an elastic collision. Momentum is conserved for both, but only energy is conserved for a perfectly elastic collision. Then we also have inelastic collisions. A perfectly inelastic collision occurs when some object's moving, it hits another object, and they stick together and move off together. In that case, energy is not conserved, or at least kinetic energy is not conserved. But momentum is. So keep that in mind when you think about collisions. Do I have an elastic collision? Do I have an inelastic collision? The next thing that we can ask ourselves is, how does an object get momentum? The way that an object gets momentum is it has a force applied to it over a certain amount of time. And that equation is going to be the next equation. This equation says that the total force acting on an object times the amount of time that force acts on the object is going to be equal to its change in momentum. The last equation I have written here is actually something that I already really talked about when I was talking about elastic and inelastic collisions, and that's conservation of momentum. So we know, again, kind of intuitively, that momentum can be transferred between objects. And so what momentum conservation says is, if I define an initial state and a final state, the sum of all of the momentum in the initial state is equal to the sum of all of the momentum in the final state. So that's going to be it for this video. The next video is going to be about fluid dynamics and thermodynamics. So just a quick note, like I mentioned in the previous video, I'm not going to do a video for the equations in rotational motion, because I had those, I went to even more detail for the third exam. So if you have any questions about those, you can reference the videos that I posted back then. Okay, so I'll see you guys in the next video. I never know how to stop this.